Welcome back, everyone. So now we'll have another talk by Kevin Buzzard on building an algebraic hierarchy.
Hello. I've got a small screen. I need to minimize everything. Right. Is my audio okay? And can you see the lean?
Yes, I can hear you, and I can see VS Code.
Wonderful. So I'm not going to talk hardly. I'm just going to whiz through this file, and then I'm going to pass it over to you. So I guess the key thing you need to know that you're probably picking up by now is that you need to start with you need to get this file, and I only uploaded it 15 minutes ago. And so, in your Lean for the Curious Mathematician 2020 folder, in the project folder, you need to type git pull and then lean project get mathlib cache. So git pull will get the lean files, and lean project get mathlib cache will get the olean files. And if you do that, you will be able to find in exercice source. It looks French to me, but in the source code for the exercises on Wednesday afternoon, there's two files, and I'm going to talk about the algebraic hierarchy, and then after me, Alex is going to talk about the topological hierarchy. So what we're doing here is we're finally going to do some kind of undergraduate level mathematics.
So can I ask a question about the
sure.
instructions so far? Do you have to close VS Code before doing the Git and Lean project, or will it automatically?
You don't have to close
adjust?
VS Code, and you could even do git pull within VS Code if you do this and then click on those dots.
Right. Okay. But you
thing.
can't do the second one from within.
No, we haven't written a Lean project Git VS Code interface yet, or something.
Okay. All right. Thanks.
But the second line is probably not necessary if you have version, just for to make sure.
Patrick is absolutely right. You might not even have to do this. It might work fine. So if you want to live life on the edge, you could probably just click here on that little Git thing, click here on these dots that I can't get to because something's in the way that you can't see and I can, some stupid Zoom thing. But if I could get to and then just click pull, everything might work fine.
Have you changed the file since this morning, Kevin?
Yeah, I changed it 15 minutes ago. It's now ready. I think the one this morning might have had all the answers in or something. So yeah, maybe a good idea not to change. So let me just whiz through what we have here, and then we can go straight to the breakout rooms and get going. So Patrick said he wanted me to give an example of something. So I have imported the rational numbers just so I can prove that we can prove something about the rational numbers. And then I import tactic because I'm going to use lean tactics. So what's this talk about? What are we going to do? So Floris this morning showed us how to make structures, and some of them were quite abstract computer science structures, but we want to focus on mathematical structures, and in particular in this talk, we're going to focus on what computer scientists call the algebra hierarchy, or the algebraic hierarchy, which is what we tend to call groups, rings, and fields and stuff like this. There's also a sort of topological hierarchy and an order hierarchy. The order hierarchy has partial orders in and lattices, and the topological hierarchy has metric and topological spaces in. So I'm going to show you how to set up the algebraic hierarchy, and I'm going to set it up in basically the same way, essentially the same way that Lean sets it up. And one big problem with doing this is that Lean has groups already, right? If I put check group, then I don't get an error, unfortunately. Lean knows what a group is, and I want to redefine groups. So the way this namespace thing works is that we're going to do everything in a namespace. So everything I define will actually be called LftCM. I'm going to define groups, but they're really going to be called LftCM.group. So they won't clash with the Lean's definition of a group. So I mean, you can feel free to read all this at your leisure. Some of this is not, some of this is not completely relevant, but it's all, it's all interesting information. So I'm going to use notation type classes. There's some magic that enables me to use this star symbol to do multiplication in groups. And I'm going to define, here's the definition of a group. I mean, you maybe, if you watched Floris's lecture this morning, you saw a different definition of a group where G was down here, where all of this stuff, G and the multiplication and the identity and the inverse, were all part of the class, whereas we've taken G out of the class. And so this definition here, we don't have a type called group, and a term of type group is a group. What we've got here is G as a type, and group G is the type of group structures on G. So a term of type group G is a group structure on G, which will mean a multiplication, an identity, an inverse, and then these three axioms. So this is set up in a way, the computer scientists call it a semi-bundled way, I think. So this is semi-bundled groups. And Floris showed you bundled groups. And they're a slight pain to work with. For some reason, semi-bundled groups are easier to work with. So this is the way it's done in MathLib, via semi-bundled groups. And one great advantage is that my axioms here, they look exactly like the way you'd write them on the board. A inverse, I'm using all the notation here, right? A inverse, that's notation for the inverse function. There's the, Floris probably had to use op, whereas I get to use multiplication and 1 for the identity element. But of course, so the advantage is it looks much more readable, but the disadvantage is that we are bound to multiplication here, right? What if I want to group with the group law addition? I'm going to have to do everything again. And indeed, that's exactly what's done in Lean. We also have a class called add group, where the group law is addition and the identity is 0. And the inversion function is neg, the negative sign. So you might imagine that's a pain, because every theorem about groups you have to prove twice, once for groups with multiplication, once for groups with addition. But we have a meta program which is written, which translates theorems about groups with multiplication to theorems about additive groups with addition. And I won't go into the details of that, but suffice it to say that I initially thought that this would not scale very well, but actually we've done fine so far. So there's the definition of a group.
In the definition of a group, where is Lean getting has mul and has one and has in from? It obviously knows what they mean.
Well, yeah, no, hasmul is already, if I right click on it, you can see there. Hasmul is, here we are, right in the depths of the file core.lean, in the middle of core lean. We've got a hasmul class. And you see, look, there you see, this is the one that causes so much trouble on Twitter. Look, the hasdiv class takes 2 terms of type alpha and returns a term of type alpha. And so in particular, you're going to have to allow 1 divided by, if you want to make fields the hasdiv class, then you're going to have to say what 1 divided by 0 is.
Okay. So
and then here's all the notation, you see. Yeah. So there's a class called hasmul, and to make a term of type hasmul, you have to give a multiplication. This is a map from alpha squared to alpha. And then a key part of this story is the notation here. The multiplication sign is defined to be hasmul.mul. So all of these are notation type classes. And a bit later on in the file, I'm going to set up another notation type class. As you can see, all of these type classes only have 1 alpha somehow. And we're going to see when a ring acts on a module, we're going to need a different notational type class. So yeah, these are all defined in core lean. Has one and has.
There is no problem with whether we denote the group operation by multiplication symbol or addition symbol.
Well, here to define a term of type group G, we have to use multiplication. I've built that in, and if you don't like that, you can see what Floris did this morning, which is another way of setting things up. But this is all an implementation question, a question that mathematicians aren't very well equipped to answer. But the computer scientists tell us that this is the best way to do groups in Lean, and so this is the way it's done. And a disadvantage of doing it this way is that we're now stuck we're now stuck with the group law being multiplication. However, the computer scientists have come up with a solution to that. If we want the group law to be addition, you know, they've written some meta code which enables every theorem you prove about groups, the meta program will translate it into a theorem about groups with group law addition. So I don't really need to go into that, but you know, that's the disadvantage of this approach. But we've been using this for years, and it's worked fine so far. So here we go. So now I'm in the group namespace. That's where all the group theorems live. So you see, you might wonder, how do you access these things? Mullersock and one mull and mull left in. They're all, if I, you see, they're all here. Look, I can check group.mullersock. There, that's the definition. You see, its actual name, I write it as mullersock, but its actual name is group.mullersock. And its actual name is, of course, if I hover over it, you can see its real actual name, which is LftCM.group.mullersock. But there it is, it's group.mullersock. And now I'm in the group namespace. And so now I can just call it mullersock, you see. If I check mullersock, there, I wonder if we get the right one. We do, there. We get, that's the multiplication that's the proof of associativity of multiplication, which I've just defined, because you can see it's got this funny thing in front of it. So all the time I'm wrestling against the problem that Lean already has a mullersock, you see. This will become slightly problematic later. So now here we are in the group, namespace, and we've got these three theorems already, group.mullersock, group.onemull, and group.mullleftinv. And now we have a bunch of exercises, which is to make a proper interface for groups. And in contrast to normal exercises in a maths book, these exercises start hard and get easier because, of course, when we only have very few axioms, you know, for example, we want to prove mull 1. We want to prove that A times 1 is A, but that's slightly difficult to do. Somehow, once we have a few familiar-looking axioms, we can start writing familiar looking proofs. But this is typically the exercise for kind of the advanced students in an undergraduate group theory course. If you only use these three axioms, then how do you prove A times 1 is A, and how do you prove that A times A inverse is 1? And you have to be careful. If you swap one of these around but not the other, then in fact you can't do it, right? But I think I've got these right. Well, I must have got these right because I checked, because you can look at the answers and see I've done it right. So now we need to prove some more theorems in the group namespace. So that's your job. So I've started you off with the first one here. This is like the longest proof. We're going to prove mull left cancel. If A times B equals A times C, then B equals C. And in contrast to most proofs you might have seen, this is not in a begin-end block. This is a different kind of proof. This is a proof in a calc block instead. So we have this hypothesis that A times B equals A times C, and we want to deduce that B equals C. And we're gonna do the stat. We're gonna do B is 1 times B. That's because, you know, that's the axiom we have, right? 1 times A is A. So B is 1 times B, and then you change 1 to A inverse times A. Then you use associativity, and then you change A times B to A times C, because that's our hypothesis. And then you go back the other way, and that's the end of our proof. So I've left you to do that yourself. By means go back into the by is the same as begin end. I put by, but I could have put begin, rewrite 1 mull end there. And so I've left you to figure out what the rewrites are. Each one of these is solvable with one rewrite. And then we'll have proved mull left cancel, which is kind of key. And then the other key thing we need is mullec of inv ek mull. We need to know that if x is A inverse times y, then A times x is y. And the proof of that uses mull left cancel, and then it's not so difficult. And armed with mullec of inv ek mull, we can finally prove mull 1 and mull right inv. And so that's what we do. That's what we do next. So, and then you see things get much easier. So let me talk about the proof of mull 1. This is kind of interesting. I've used the simplifier, right? When I started learning Lean, I thought the simplifier just meant prove all simple things. But of course, life isn't remotely as easy as that. The simplifier, this is a fancy rewriting system. This is a confluent, this is some kind of rewriting system that computer scientists understand very well. And the idea is you have to train it with equalities. So I've explained a little bit about the simplifier here. The idea is I'm going to tell the simplifier, one mull says that 1 times G is G, and that's one of the axioms. And mull left im says that G inverse times G is 1. And both of these are equalities, And the key fact about them is that the left-hand side is more complicated than the right-hand side, right? Equality is not remotely a symmetric. You shouldn't think of equality as being a symmetric thing in Lean. You really don't write 1 mul G to be the same as that G equals 1 times G. That would be a disaster. I mean, not a disaster, but very inconvenient. We write it as 1 times G is G, and then we teach it to the simplifier. I've tagged it with the simp attribute. And what's happened now is that now when Lean sees 1 times G, if you run the simplifier will change all 1 times G to G, and it will change all G inverse times G to 1, you see. And so this proof of mul 1 here, we apply a lemma that we proved already, and then the goal becomes 1 equals A inverse times A. And I've trained the simplifier to recognize that A inverse times A is 1. So the simplifier then solves this goal. If I comment this out, you see, if I don't train the simplifier here, then the simplifier fails. I have a red error message. And if I put this back, then it works again. And I've also told this thing here means let the simplifier know that A times 1 is A. So now the simplifier knows that 1 times A is A, and the simplifier knows that A times 1 is A. You see, this is much more like mathematics. In the natural number game, x add 0 is x is true by definition. 0 add x is true because of a theorem. It's not definitionally true. So there's some weird asymmetry here. But we're teaching the simplifier A times 1 is A and 1 times A is A. And the simplifier treats them as equal. You know, they're the same as far as the simplifier is concerned.
Kevin, can you
Hello.
Can you put the simplifier attribute in the class definition?
Yeah, no.
That would seem to be a natural thing to do.
I don't know. Yeah, I've all of those things. I'm going to teach the simplifier all 3 of those axioms. I don't know. That's a question for an expert. Is there a way of teaching all of the axioms to the simplifier? That's the kind of thing that you mentioned to Scott Morrison, and like a day later, there's a pull request to MathLib with some fancy way
Scott
of
already
using it.
did this job. So yes,
Sorry?
Scott already did it.
There you go. Scott already did it. So the answer is yes, but I don't know how to. Tony. So yeah, so now we can train the simplifier, and we know we want to train it on, you know, we want to tell it equalities of the form A equals B, where A is more complicated than B. So here's a dumb group theory question. What do I do? Control that. Here's a silly group theory question. Both of these, there, I can't even see it. Let me do this. Could you prove that this equals this? I mean, I think both of these are kind of trivially equal to the identity. If you're a human, right? If you're a human, you could look at that and you know exactly what to do to check that this is the identity, because you know that A times B inverse is B inverse times A inverse, and things cancel. And you know, this is all just 1 inverse is obviously 1. But you see, the simplifier can't do this yet. The simplifier needs to be trained a lot more. And computer scientists kind of understand exactly which lemmas you need to prove. So here's all the lemmas you need to prove. The inverse of 1 is 1. The inverse of A is A. These are all things we're going to train the simplifier to do. We're going to tell the simplifier associativity of multiplication. And the bad thing about telling it associativity of multiplication is that now it shunts all, associativity of multiplication says this, it shunts all brackets to the right. And so you end up with situations like this, when all the brackets have been shunted to the right, and now Lean can't cancel the A inverse and the A, because the A inverse and the A aren't in somehow one bracket, because the simplifier moved all the brackets to the right first. So we have to train the simplifier to solve this goal here. A times A, the way to prove it, of course, is just we rewrite Mullersock, right? We move the bracket back to the left, and probably the simplifier will now do it. You see, there you go. There's a hint. You see, once the simplifier knows that it shouldn't have done that, then it's kind of easy. Sorry, I'll remove the spoiler. So there's some things there, and then finally you train the simplifier to show that A times B inverse is B inverse times A inverse. This is a slight challenge to prove from the axioms, but once you've taught it these things, Knuth and Bendix proved that these lemmas that we have here are precisely what you need to make the simplifier become a normalized rewriting system. And so you can read about confluent rewriting systems if you like, but as you can see here, we've got our example again, this sort of silly pathological example, some silly thing equals some silly thing, and the simplifier has solved this for us. So the first part of this the first part of this file is to show you how to train a simplifier. And it's sort of a very interesting question in general, how far you can train the simplifier. But we've now trained the simplifier, to solve the word problem in 3 groups. That's basically what we've done here. And, a theorem of Knuth and Bendix is that these lemmas are precisely all you need to do that. So there's a fun thing, train the simplifier. Next thing, let me prove that the product of 2 groups is a group. So Floris did this with the bundled group, with bundled groups. But here's, one can do this in the unbundled situation. And I should say I made group a class. Maybe Floris talked about classes. I didn't just make it a structure. I made it a class. And that means make it a structure, but let the type class inference system know about it. And so the type class inference system knows about groups, and it's keen to hear about ways of making groups. And you train the type class inference system using instances. So down here we have an instance. So if G and H are groups, then I claim that G times H, the product of G and H can be made into a group. But instead of making this a definition or a theorem, I make it an instance. And then I just go through the proof here. You can read the proof yourself and figure it out. There's a couple of stories I left for you. But now you see the clever thing is now, this invokes the type class inference system. So now I say, now if I've got 3 groups, G, H, and K, then can you find a group structure on G times H times K for me? And the type class inference structure says, sure thing. This tactic here says, use the type class inference system to try and make this a group. And the reason it works is because we've made groups a class. I found the type class inference system incredibly complicated to understand, by the way, I should say. So here's one last example with groups. I've shown you how to make a group of order 2. So I define a new set mu2 with 2 elements, p1 and m1. I mean, these are really, these are terms of a type. But basically, mu2 is a set with 2 elements. And I magically prove that equality is decidable. And I magically prove that it's a finite set. And then I define multiplication by writing down all the cases. And I define the identity to be +1. And I define the inverse function to be the identity map. And then I show you that we can make it a group. Just, you can, what I'm showing you is we can do abstract things with groups, like prove that the product of 2 groups is a group, but we can also do concrete things with groups, like make a new group. We could make symmetric groups like this as well, for example. So that's all the groupy part, which is kind of the first half of it. And then the second half is just really a demonstration about how these classes can be glued together. So there are fewer exercises here because it was a pain to write them. But you see, there's the definition of a monoid. We're not really into monoids in maths departments, or most of us aren't, but it's just a group without inverse. And there's the definition. You see, I've defined a group, but I've had to define an additive group, make another class. There's the definition of a commutative additive group. So I'm extending additive notation here. And so once we have monoids, why did I even do monoids? Who cares about monoids? We have a monoid and an additive commutative group. That means we can make a ring, you see, because rings just extend. A ring is a monoid and an additive commutative group that satisfies the distributivity axioms. So now we have rings, and of course we can make commutative rings because they just, we just throw in an extra axiom. You see how easy the whole thing is. And now here, John earlier was asking about scalar multiplication. I've had to define a new type class of scalar multiplication because I want scalar multiplication given an element of a ring and an element of a module. I want to multiply them together, but they don't have the same type. So I've defined a new scalar multiplication type that takes an element of a ring and an element of a module and spits out the element of a module. And here's my, I've made the notation dot for this thing here. And so now I can extend this has scalar notation and write down the axioms for a module. So I just copied these off Wikipedia. So hopefully they're right. And there's my axioms for a module. And I've made modules over a ring. And so now, for example, I can make ideals of a commutative ring by just saying an ideal of a commutative ring is a, that's not even right. That's not right. That should go. Sorry about that. I should make I haven't made, I need to make submodules to make ideals of a ring. That's tomorrow. I'll be making submodules. Here's a field, which is a commutative ring with an inverse. This is sort of an interesting definition of a field because it's not quite what a mathematician would expect. A field is a commutative ring with 0 not equal to 1 Everything's got a multiplicative inverse apart from 0. And we also define the inverse of 0 to be 0. So this is really quite counterintuitive. But the problem is this has_inv is a type class that's defined on the whole type. So the moment I make k an instance of the has_inv type class, then I can take the inverse of every element of k, every term of type k. And so what we do is we simply demand that the inverse of 0 is 0, and the inverse of any non-zero thing, when you multiply it together you get 1. So there's a field. And now, of course, we can just define a vector space over a field just to be a module over the corresponding ring. Do you see this is quite, you see Lean is doing clever things here. A field extends a commutative ring, and a commutative ring extended a ring. You see, I said, let's let, you know, I'm going to define a vector space over a field to be a module over that field. But this module thing, if I hover over it, you can see that Lean expects K to be a ring here, right? Lean expects K to be a ring, but I've given it a field. So how does Lean know that a field is a ring? That's the type class inference system again. It's doing it all by magic there, because I said field extends com ring. So the type class inference system learned that a field was a commutative ring, and com ring extends ring. So the type class inference system learned that a commutative ring was a ring. And so what's happening here is I say, K is a field, now pretend it's a ring. The type class inference system, because it's in square brackets, the type class inference system finds the proof that K is a ring, or the instance of type ring K, from the fact that it's a field. And so now once you built all of these things, of course, now you can, you know, there's some, you can just go on and build, you know, I built, as maybe people might know, you know, I built schemes and perfectoid spaces in Lean with Patrick and Johan. Well, I built schemes with Kenny and Chris, and perfectoid spaces with Patrick and Johan. And now Sebastian and many other people are making manifolds. It's not so difficult to make these things. You just write down the axioms. But the hard part is to make the interface, right? We've done all these lemmas about groups. We proved, you know, defining groups was easy, but then actually making groups work involved proving 10 lemmas about groups. So we've defined rings and fields and vector spaces and things like this. You know, there's just, I'll prove to you that the field, you know, I'll prove to you that it works. I can make the rationals into a field. This is easy because Lean already made the import at the top already made the rationals into a Lean field. And I now make them into a Lean for the curious mathematician field by just saying, oh yes, all the theorems have been proved already. You see, this field isn't Lean's. What's going on here is that the rationals are already a field, but for Lean's version of field. And now I'm proving that they're a field for my version of a field, the field I just defined here. And the proof is easy. But now, unfortunately, I finally ran into trouble because I'm always constantly having to tell Lean to use my version of zero add and use my version of add left neg. So here's me developing some of the theory of commutative, additive commutative groups. And then I let you develop some of the theory of rings, if you like. You know, if you get this far, why don't you try and prove things like R times A minus B is R times A minus R times B. So that's an overview of the file. And then finally, there's an advertisement. The same various other, you know, if you need more exercises, here's some other things you might want to look at. And also an explanation about what the Xena project is. I'm interested in teaching undergraduates about Lean. And so here's some explanations at the bottom for those who are interested. Right, that's all I have to say. And now feel free to try and prove that, try and construct a normalized complement rewriting system for groups from first principles, because it's not that difficult and it's quite good fun. This is another thing the undergraduates quite like doing. Okay, I've said enough. Hopefully somebody can now
okay, thanks a lot, Kevin.
Their rooms.